Hello class. We're going to look at section 4.5, how concentration and things are measured in the laboratory. Quantitative chemical analysis. It describes the fundamental aspects of titrations and gravimetric analysis and performs stoichiometric calculations using typical titration and gravimetric data. Let's go to this. We will discuss two main types of quantitative analysis, titration and gravimetric analysis. Titration is using liquids to determine the concentration of something. So you'll have like a standard liquid in a pipette. And gravimetric analysis is precipitating something and then filtering the precipitate, drying it, and weighing it. Titrations involve two solutions: the titrant, the solution containing a known concentration of one reactant, and the analyte, a solution containing a reactant of unknown amount or concentration. Measuring the volume of titrant solution required for one complete reaction with the analyte, the equivalence point of the titration, allows calculation of the analyte concentration. Okay, that means to say that we measure the volume of the titrating solution until we reach a point that can be detected where the titrant and the analyte have completely reacted with one another. And then this allows for the calculation of the analyte concentration. The most simplest one is the reaction of acid with base. A common titrant would be sodium hydroxide, a strong base, and an analyte might be an acid such as acetic acid and vinegar. And you put in a indicator solution like phenolphthalein, or phenolphthalein would be a good one, that turns bright pink in the presence of alkalinity. And so you keep adding the alkaline material until the acid is completely used up, and then the alkaline material is expressed in solution and turns the phenolphthalein pink. Okay. Indicators are added to the analyte solution to impart a change in color or very near the equivalence point of the titration. The volume of titrant actually measured is called the end point. The difference between the equivalence and endpoints should be negligible. So here's a man filling a burette with something bluish so that you can see it. And this shows how one measures the burette. A student fills a burette in preparation for a titration analysis. A typical burette permits volume measurements to the nearest 0.01 milliliters. So you see the gradations, this is 1 milliliter. The gradations are in tenths of milliliters, and you can read between the lines to get at something that's in the hundredths of milliliters. The end point of a titration of a 50 milliliter sample of aqueous HCl was reached by the addition of 35.23 milliliters of a 0.250 molar sodium hydroxide titrant. The titration reaction is hydrochloric acid aqueous plus sodium hydroxide aqueous goes to sodium chloride aqueous plus H2O liquid. What is the molarity of the HCl? They also added to this something like an indicator like phenolphthalein, and as soon as all the hydrochloric acid was used up, just a tiny amount of sodium hydroxide was now in excess and turned the phenolphthalein pink. That's how you knew it was at the end. What is the molarity of the HCl? Well, the equation for this, adjusted for stoichiometry, is very similar to the dilution equation. And that is that the volume times concentration of the titrant is going to equal, if it's a one-to-one reaction, only if it's a one-to-one reaction, the volume times concentration of the analyte. And so in this case, this times this is going to equal 50 milliliters times the concentration of HCl in molarity. And we'll see that. So here we've got the volume of NaOH times its volume gives you the moles of NaOH. Then using the stoichiometric factor, it gives rise to the moles of HCl. And then multiplying that by its volume times molar concentration equals moles, stoichiometric factor, moles of HCl times its solution volume yields concentration. So effectively, we've got volume times concentration equals the volume times concentration, and the only thing we don't know here is concentration, and so it's just like the dilution equation. This many milliliters of NaOH, we don't even need the factor of 1,000 here, times 0.25 molar equals, no, well, hold on. This is just calculating the moles of HCl. And then from the moles of HCl, we divide by the milliliters and we get molar concentration. Gravimetric analysis. This is the type of analysis in which a sample is subjected to some treatment that causes a change in the physical state of the analyte that permits its separation from the other components of the sample. So, like precipitation. Mass measurements of the sample, the isolated analyte, or some other component of the system used along with known stoichiometry of the compounds involved permit calculation of the analyte concentration. Commonly, the analyte is separated by subjecting it to a precipitation reaction. So the precipitate may be removed from the mixture by filtration. A 0.455 gram solid mixture containing magnesium sulfate is dissolved in water and treated with an excess of barium nitrate, resulting precipitation of 0.6168 grams of barium sulfate. What is the concentration of magnesium sulfate in the mixture? So what we know is that we calculate the number of moles of barium sulfate that is produced, and that will tell us how many moles of magnesium sulfate that we had, and then from there we would calculate its mass and then divide it by the 0.4550 grams times 100% to give the concentration. So here it is. The mass of barium sulfate divided by its molar mass is the moles, times the stoichiometric factor gives the moles of, should have been magnesium instead of calcium. And from the moles of magnesium sulfate, using its molar mass, we calculate its mass. And then from its mass divided by the mass of the sample, we get the percent magnesium sulfate. They do it right on the bottom. They didn't change the picture. And we get 69.91%. The elemental composition of hydrocarbons. Okay, this is combustion analysis. Well, I was telling you about combustion analysis when it had to do with the empirical formula. Well, this is how we know what the empirical formula for compounds is. We subjected to combustion analysis. The elemental composition of hydrocarbons and related compounds may be determined via a gravimetric method known as combustion analysis. A weighed sample of the compound is heated to a high temperature under a stream of oxygen gas, resulting in its complete combustion to yield gaseous products of known identities. The complete combustion of hydrocarbons, for example, will yield carbon dioxide and water vapor as the only products. The gaseous composition products are swept through separate pre-weighed collection devices containing compounds that selectively absorb each product. The mass of the absorbed product can then be used in an appropriate stoichiometric calculation to derive the moles and mass of the relevant element. So here the sample is in a furnace, we call it a tube furnace, with oxygen flowing over it, and then this reacts to form carbon dioxide, water, and it has oxygen and perhaps other gases. Well, the water is absorbed in the first section, and the carbon dioxide is absorbed in the second section. I believe nitrogen can also be analyzed this way. Anyway, and then the oxygen in the compound is determined by difference. Polyethylene is a hydrocarbon polymer used to produce food storage bags and many other flexible plastic items. A combustion analysis of a 0.00126 gram sample of polyethylene yields 0.00394 grams of carbon dioxide and 0.00161 grams of O2. So, if it had this formula, C with the X on the bottom and H with the Y on the bottom, and it reacts with excess O2, it'll produce X number of grams, X number of moles of carbon dioxide and Y over 2 moles of water. What is the empirical formula for polyethylene? Well, so it produces this many grams of carbon dioxide, and so you'll divide that by the molecular weight of carbon dioxide, which is 44, to get the number of moles. Divide this by the 18 to get the molecular weight of water, and you'll have to multiply it by 2 in order to get the amount of the moles of hydrogen that are in there. And from all of that, we have the crude exponents, and then dividing by the smaller of the two, you can get the empirical formula exponents. So the mass of CO2 divided by the molar mass gives the moles of CO2. Stoichiometric factor gives moles of C, which is in this case is 1 to 1. It gives them and would result in the mass of C. The mass of H2O divided by its molar mass, which is 18, gives the moles of H2O, times the stoichiometric factor, which is 2, gives the moles of hydrogen atoms, which can go to the mass of hydrogen atoms. But both of these, and I needed a connector right here, go to the C to H mole ratio into the empirical formula. And so it's all carried out. So you get that number and you get that number for the moles of carbon and the moles of hydrogen. And you divide by the smallest of these numbers, which is the moles of carbon. And so we get 1 mole of carbon to 2 moles of hydrogen. So the empirical formula is CH2. The number, we did this in class, and so on and so forth. Well, I thank you for your time. Let's get out of this. Bye-bye.